before we start talking about some more advanced topological concepts, we need to establish some fundamental definitions. So in this video, I'll have 4 definitions that we need to proceed. The first of which is the definition of a neighborhood. Now, a neighborhood is kind of a weird concept the first time you see it. I should say the neighborhood of a point, because you have to specify a point in your topological space, and then you say your neighborhood of that point. Sometimes denoted n as an element of like curly n subscript a. This is the collection of all neighborhoods. Sometimes I abbreviate neighborhood NBHD. So curly n sub a is the collection of all neighborhoods of A. So sometimes we'll use that as a shorthand to just say n itself is a neighborhood of A. If the following is true, you have an open set. So there exists some u in tau, some open set u, such that A is in U and U is a subset of N. Okay. Kind of weird to look at. Literally all it means, if you're given some space X and some point A, so A here, we say that N, and maybe I'll draw N in purple, and I'm going to draw N weird. It's going to be some crazy blob that's like open on some parts of it and closed on some parts of it, because I want this to be general. We say that N is a neighborhood of A if there exists some open set U so here U is actually an open set. It's an element of tau. Maybe I'll specify that, U is in tau. That's fully contained in N, while also containing the point A. Sometimes you'll call U an open neighborhood. But that can confuse people, because then you're talking about neighborhoods in terms of open neighborhoods, and it's a whole thing. So yeah, suffice it to say, N is a neighborhood of a point if there's an open set containing A fully contained within N. Okay, and then from there, with that definition of neighborhood, you can define some very important concepts. The first of which, different people have different notation for. Some people write CL. Some people use the overbar notation. But in either case, they're talking about the closure of a set. So the closure of a set, you can define it in terms of neighborhoods, or you can define it in terms of open sets, whatever you like. The closure of a set is sort of what you would expect from your knowledge of metric spaces. So let me draw something instructive here. Let's say, again, I'll use purple. Try to draw the same kind of thing, some blob here. This time we'll call it A. So A is some subset of the topological space X, and the closure is the set of all points that are adherent to A. I haven't defined adherent. Adherent means that whatever neighborhood you take of the point A, or the point X, I guess I should say. Yeah, let's rewrite this. That was supposed to be an X. X is adherent to A if any neighborhood of X intersects A. The way I like to think about it is, let's say I had some point, let's draw it down here. So let's say that's the point, let's write X. If that's the point X, then it has to be true that no matter what neighborhood I draw around X, it still intersects A. Right? X itself might not be an A. I drew it on kind of the open boundary on purpose. So maybe X isn't an A, but every neighborhood of X has to touch A, has to intersect it non-trivially. So the way you can see that, and sometimes it's easier just to phrase it in terms of open sets and say, instead of all neighborhoods intersecting A, just say all open sets containing X intersect A. So you can see that, no matter what open set I take, there's U, guess what? It intersects A. Ta-da! Or if I go even smaller, say I really tighten my grip, and that's my set U. Well, guess what? Again, U still intersects A. And no matter how small you shrink that set, that open set, you're still going to get some intersection. And so it doesn't really matter if you think about this as a neighborhood N, or you think about it as an open set U. It's going to be the same story, right? That's a point of confusion for some people, right? If things are phrased in terms of neighborhoods, or they're phrased in terms of open sets, how do you connect the two concepts, right? Well, the answer is whenever you're given a neighborhood, you automatically have an open set contained in it. So really, it's sufficient just to consider all open sets. And sometimes I'll skip ahead and really just think, forget the neighborhood, just think in terms of open sets. So yeah, a point of closure or an adherent point is just something around which all open sets intersect the set A. So take some time to digest that definition. It's just kind of a weird one. The next definition is that of interior. And again, you can define it in terms of neighborhoods, but I prefer not to. I'll show both, but I feel like the neighborhood just obscures what you're trying to get at. So again, let's draw this weird blob. Oh, and by the way, I didn't exactly draw the closure. The closure of this set A would have been everything in A plus the boundary points that we missed out on. That would have been the closure, right? Because I could have made the same argument that I made for this yellow point X for any point along here. And so all points that were left out of A, you could think about them as limit points, but usually you don't define things that way in topological spaces. But they're in some sense close to A, right? That was when I first talked about topological spaces. I said, you won't have a distance metric, but you'll have some way of knowing closeness. And this is that way, right? The fact that every open set intersects A means that point has to be close to A. Okay, so similarly, the interior is defined, it's defined pointwise. So no matter what point A you pick, so I could pick A here, the interior is the set of points for which you can fit an open set entirely within A. Sort of be sort of similar in some ways, dissimilar in others. But it should kind of make sense. If you're a point existing in a set, then you're interior to that set if you can put some neighborhood around you. Right? So again, you can think of this as a neighborhood N, or you can think of it as an open set U. I don't care. Both of them end up being equivalent. But yeah, there has to exist some open set that you can kind of nestle in there so that it doesn't break out. Now, something that's not in the interior would be like something on the boundary here. In this case, A would not be in the interior because no matter what open set I put around A, there's some part of that open set that's outside of A. I forgot to label this at A, but I think you know by now the purple is the set A. Okay, so that point in the bottom right is not interior to A, because no matter how small your open set gets, it's gonna fall outside of A somewhere. So what does that mean the interior looks like? Well, it means the interior is, well, it's correct here. Right? This side was like open, so that's fine. But then it misses all the boundary points. So I'm going slightly inside that solid line. Okay, that's correct here. And then slightly inside the solid purple. That's what the interior looks like. And that's really how you should reconstruct these definitions. You should never memorize these things. You should just think, okay, a point of closure is something that, right, so don't memorize these, do memorize these. Although memorize is a weird word. You should really find it intuitive that a point of closure is something that's really, really close to A. And a point that's interior to A is something that's like so well inside A that you could actually fit a ball around it. I'm saying ball, but I really mean open set. Okay, and then the last concept we have is the concept of boundary. I've been using that in a kind of hand-wavy way, but there's a formal definition, and there are a lot of formal definitions, really. This is just the one I like, that the boundary of A is the closure minus the interior. And that gives you sort of exactly what you would want. The interior was, you know, this dotted bubble here, plus everything inside of it. The boundary would have been just the dotted bubble, as the name suggests. So basically, you're a boundary point if you're really close to the outside of A, but not on the inside of A. Right? You're exactly on the boundary. And so let's see some examples of these things. Right? It's good to have the geometric pictures, but it's good to have some concrete examples as well. So let's say we're working in R, okay, with the usual topology, meaning the Euclidean topology. Then let's consider the half-closed, half-open interval from 0 to 1. So that set looks like this. So including 0, not including 1. The closure is sort of what you would expect. Right? Again, we're working with the usual topology, so you can think about this in terms of metric spaces. And if you want to think about limit points, in this case, it's fine, because usual topology on R gives you a metric space. So what would you expect? Well, the only point that's missing, the only sort of limit point, would be this, would be 1. So the closure is the closed interval from 0 to 1. And yes, in general, the closure is always closed, even in topological spaces. The interior, on the other hand, well, what happens to this point? 0 is not on the interior, because no matter what ball I put around it, I'm ending up outside of the purple set. That's certainly not an interior point. Whereas every other point, sure, I could put a ball around that. I could put a tiny little ball around this. Again, when I say ball, I mean open set, but they're equivalent when you talk about metric spaces. And so the interior would just be that, the open interval from 0 to 1. And what does that mean for the boundary? And remember, the boundary is the closure minus the interior. So that point's boundary, that point's boundary. You just get a set of 2 elements. All right, so that agrees with intuition, hopefully. The other weird thing is if you deal with the rational numbers, the closure of the rationals is the set of real numbers. That means that no matter what rational number you pick, you could think about the rationals sort of densely packed within the real line, and no matter how far you zoom in, you can find more and more rationals. And so again, that's sort of like saying, well, no matter what rational point I'm considering, say this one, if I put some open set around it, then yeah, I'm going to hit some other rationals. And even if I pick some irrational, say this is pi or something, and I put some open set around that, guess what? Ding, 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 ding. I hit infinitely many rational numbers. And yeah, no matter how small I shrink that interval, I'm hitting arbitrarily many rational numbers. So that goes to say that the irrational numbers are arbitrarily close to the rational numbers, meaning the closure of the rationals is the whole space. Whereas for the interior, well, are any points interior to Q? No, I mean, if I pick, let's use purple. If I pick, say, this point, let's say that's the point, I don't know, 9/2 or something. That's a rational number. Is it possible for me to squeeze an open set around it that's fully contained in the rationals? Well, no matter how small I squeeze it, there's still going to be some irrational inside of it. For example, 9/2 minus pi over 1,000, right? Pi is irrational, so 9/2 minus pi over 1,000 is irrational, and it's within that interval. And no matter how small I squeeze that interval, I'll still find irrational numbers, so the interior is nothing. And weirdly, that goes to say that the boundary of the rationals is everything. Every point is a boundary point, because every point is, or every real number is arbitrarily close to a rational number, but no real number is like nicely nestled within the rationals. Right? They're all on the edge. They're all about to fall off into irrational territory. And maybe you've seen that in analysis. Let's try something with some of the new topologies we've learned. So for example, the discrete topology. So let's say we have the discrete topology defined on X, and we have some subset A of that space. Then what can we say about the closure, interior, and boundary of A? Well, the closure of A is itself. The interior of A is itself, and the boundary is nothing. It's easiest to start with the interior. The interior of any open set is always itself. Okay, one way you can think of the interior is the smallest open set contained within your set. And hopefully that agrees with your intuition from back here, that the interior was like the smallest open set I could draw within A. And okay, if we're dealing with the discrete topology, as in this example, if we're dealing with the discrete topology, then every set is open. So in particular, interior of A is A. How about the closure then? Well, something I didn't mention about the discrete topology is that every set is closed in the discrete topology. And what do you know? The closure of a closed set is itself. So in fact, yeah, I mean, any subset in the discrete topology is closed because its complement has to be open, because everything's open. Does that make sense? Remember that tau is everything. Tau is the power set of X. So every subset is open actually means every subset is closed. because you find the closed sets by taking the complements of open sets. And I told you there was a one-to-one correspondence between open sets and closed sets. So yeah, if every set is open, then every set is closed. And so that means the closure of every set in the discrete topology is itself. It's already a closed set. And then use your formula, closure minus interior. Well, there's nothing left. There is no boundary. So in the discrete topology, there are no boundary points. Whereas in the indiscrete topology, everything is a boundary point. But this is kind of similar to the rational numbers within the reals, in that if you're given some subset A, and here, just to make things nice, I'm requiring A to be non-empty and a proper subset of X. So I don't want it to be empty or the whole space, but any other subset works. Then it turns out that the closure of A is everything. And this comes from the fact that the closure of a set is sort of the largest closed set containing it. Right, again, going back up here, the closure of A, I kind of drew it as the largest closed set containing A. There's a formal way to explain that, but whatever. What is the largest closed set containing any subset? Or I meant to say smallest. Sorry. What's the smallest closed set containing it? Well, it's the whole space, right? There are only two open sets in the indiscrete topology. The empty set is open and the whole space is open. So what's the smallest? I mean, those are open, means they're actually the only closed sets as well. So yeah, X has to be the smallest closed set. You know, it might not be small, but it's the smallest because there are only two options. Similarly, the interior of a set is the largest. This is why I messed up a second ago. The largest open set contained within your set. And okay, if you have some non-empty set A, the only open set contained in it is the empty set. So yeah, the empty set is largest, even though it's not exactly large. In the case of the indiscrete topology, things are pretty pathological. The largest open set happens to be the empty set. And again, applying the formula, X minus the empty set is X. So every point is on the boundary in the indiscrete topology. And then how about this one? So if we're thinking about R2, you can define a topology which is built from open disks centered at the origin. So naturally, you want to take the empty set and the whole space, but the other sets you're declaring to be open, the only other sets you're declaring to be open, are open disks with positive radius. For example, that's an open set, that's an open set, so on and so forth. Something out here would not be an open set because it's not centered on the origin. I'm declaring this topology to require these sets to be centered on the origin. By the way, what does that mean a closed set is? Well, a closed set would be something like this, the complement of an open set. Ta-da! Everything outside of a disk. So that's a weird topology. But given that topology, we could ask about the closure of a square. So I'm just defining the square S to be the set of all points in R2, where the largest of the X and Y values does not exceed 1 in absolute value. So let's draw that. To make this a less than or equal to. Cool. So less than or equal to 1. Plus everything inside. So that's what S looks like. And the question is, what is the closure? What is the interior? What is the boundary? Okay, interior is easiest to see. The interior comes from seeing that. Let me erase this inside so I can draw better. The interior comes from looking at this and saying, what's the smallest open set I can, or sorry, what's the largest open set I can fit inside S? Well, I mean, there's an open set I could fit inside S, but I could do better, right? I could get larger than that. I could do this, but again, I could do better. And maybe you think, oh, I'll do like the unit ball, right? That's an open set that I can fit inside X. And if I were to get any larger, I'd break outside of it, right? So I don't want to get any larger. So that's the set, the open disk with radius 1. So that turns out to be the interior. Weird, right? If you were doing things in the Euclidean topology, you would have had the interior being like what you expect, like the insides of the square here, including these little corners, just not including the yellow outline. But in this topology, we've predefined what our open sets are. I'm not allowed to use a square. The only open sets are disks, right? Besides the empty set in the whole space. And then how about closure? So the closure, I'll draw in red. The closure, you want to think, what's the smallest closed set that contains S? Let's remember what a closed set is. A closed set is the complement of an open set. So something like the whole plane with a disk punched out of it. Just fill that all in red. Shading, the entire plane except for that little center there. Okay, weird. So how on earth could I do this? I mean, if I go larger, then I get everything out here, but that's not containing S, right? This is a whole big vacuum in here that I'm ignoring. Even if I go really tiny, like I was just drawing, right? Tiny and then go out, then I'm containing most of S, but what about in the center, right? I'm missing like the origin, and the origin's a point in the square. The square's filled in. Ugh, okay, so what happens? Well, it turns out R2 itself is closed. So if you take all of R2, that's actually the smallest closed set containing S. So check. Because everything else will have a disk punched out of it. And that's a problem. All right, and that means the boundary is everything outside of here. So R2 minus the open disk of radius 1. Everything out here is called the boundary. So very strange that points not even in S are in the boundary. But there you go. Right, so that's our introduction to closure, interior, boundary, and it's all built off the concept of neighborhoods. Hopefully it's not too confusing. It's really helpful to have these notions that the closure is the smallest closed set containing the set you're talking about, and the interior is the largest one contained within. Thanks for watching.